Okay, in this video we're going to talk about the matrix of a linear transformation. And there are lots of different ways to explain this topic, but I'm going to explain it in the more general case where you have two vector spaces and a linear transformation from one vector space to another. So let's say that you have a vector space V and a vector space W and a linear transformation T from V to W. So let's say V is some vector space of dimension n, and W is some vector space of dimension m. Well, in a previous video, we've seen that once you choose a basis for V, so let's say that you have an ordered basis V1 through Vn, so an ordered basis for V and an ordered basis for W, so W1 through Wm, an ordered basis. For W, then such a choice of a basis defines a map. It defines a map from V onto Rn, and it defines a map from W to Rm. So you have a concrete way of understanding vectors. So it takes V, an element of the vector space V, and maps it to the coordinate vector of V relative to the basis. Let's say this basis of V1 through Vn is B, and let's say the basis W1 through Wm is C. Okay, like curly B, curly C. Okay, so you have this map that sends the vector V to the coordinate vector, which is V with the brackets and then a B on the bottom right, and then you have this map that sends the vector W to the coordinate vector in Rm, right? And the question is, so you have this concrete way of understanding the two vector spaces V and W because you're identifying them with Rn and Rm respectively. And the question is, now you have a linear transformation from V to W, say, then how do you understand that linear transformation concretely? And we want to represent this linear transformation in terms of a matrix. So that's what the matrix of a linear transformation does. So let's explain how to do it. And before getting into the general explanation, let's just do an example. So let's say that you have V is a subspace of R3. Let's say it's a plane in R3. And let's say W is also a plane in R3. So here's R3. And let's say that let's say that V is this plane. Okay, and it's also, going out infinitely, right? It's this plane, and that's V, so it's two-dimensional. So our n is 2, right? N is the dimension of V, and then W is, let's say, another plane in R3. So let's say it's this one. Let's say that's W. And so our M is going to be 2 because W is two-dimensional, okay? And let's say that hold on, where's my sheet here? So let's say that I have this vector V1, which is this vector, and some other vector V2, which is like this vector, and let's say that's my ordered basis. And let's say that I have a basis for W, let's say this vector W1 and then W2, right? So just two linearly independent vectors in each subspace. Okay, so I have my ordered basis. Now what happens is, if you have a vector V, in V, And let's say I have a linear transformation T from V to W. Now, this linear transformation doesn't have to map R3 to R3. The domain of T is going to be V, and the codomain is W. Okay, so you can have a linear transformation just defined only on the subspace. Okay, so you have a linear transformation from V to W. Well, it's going to take a vector in V to a vector in W. So let's say it's, well, actually, the way I defined it, it looks like, I have a specific linear combination of V1 and V2, right? So why don't I erase, let's make my V, say V1 plus V2. So it's going to be like this. Then it will go to W1 plus W2, which is like here. So that's going to be my T of V. Right? And I can represent the vector V as a linear combination of V1 and V2, and I can represent T of V as a linear combination of W1 and W2. In particular, oh wait, sorry, I take that back. Excuse me. I have some vector V, and it's going to go to some vector W, to some vector T of V. Okay, which actually could be out here. The thing is that I was assuming, I shouldn't have been doing that. I was thinking that V1 would go to W1 and V2 would go to W2, but that's not the case, right? I just have a basis for V and a basis for W. Okay. Yeah. So when I look at T of V1, right, that's going to be some vector in W, and so it's going to be a linear combination of W1 and W2. So let's say C1 W1 plus C2 W2 for some scalars C1 and C2. Similarly, T of V2 is going to be a linear combination, say D1 W1 plus D2 W2 for some scalars D1 and D2. Okay. Now I define the matrix of T relative to these bases so this basis for V and this basis for W to be this matrix C1, C2, D1, D2. So that's the example in this particular case of the matrix of a linear transformation. Now what's going on is you're taking, so this first column is the coordinate vector of T of V1, right? You're taking T of V1 is C1 W1 plus C2 W2, and what that means is that the coordinate vector of T of V1 relative to the basis C is C1 C2. And similarly, the coordinate vector of T of V2 relative to the basis C, so C is my ordered basis W1, W2, and B is my basis V1, V2. The coordinate vector of T of V2 relative to the basis C is D1, D2. And so that's how I'm making my matrix. So I can represent this as, okay, what's going on is I have this 2 by 2 matrix, and I take the first column to be T of V1 relative to the basis W1 and W2, and my second column is T of V2 relative to the basis W1, W2. All right, so T of V1 is C1 W1 plus C2 W2. T of V2 is D1 W1 plus D2 W2. That's how I'm making my matrix. Okay. So let's just look at a quick example. So let's say I have a vector space V, and suppose that V has an ordered basis V1, V2, and let's say that W is some vector space and it has basis W1, W2. So suppose this and that. And suppose that I define a linear transformation T, and this linear transformation sends T of V1 to 6 W1 plus 3 W2, and T of V2 is 2 W1 minus 5 W2. So define the linear transformation T from V to W by these two equations. Now once you define what T does to a basis, then there's only one linear transformation that will do those things. So this, just defining T on the basis defines the linear transformation. Okay, so this sentence makes sense. Then what's the matrix of T relative to these bases? So then the matrix of T relative to, okay, let's just call this one B and this one C. So the matrix of T relative to B and C is, well, so it's this 2 by 2 matrix. Remember I take T of V1, that's 6 W1 plus 3 W2. So the first column is 6, 3, and then I take T of V2, that's 2 W1, and then minus 5 W2. So that's my matrix. Okay, and let's just erase this because this isn't, part of the matrix, right? Okay, so that's my matrix. Let's do another example. So let's say that V is this space. It's this set of all vectors x, y, z in R3 such that x plus y plus z equals 0. So this is a subset of R3, right? 3 components. And W is the set of x, y, and z such that x minus 2y plus 3z equals 0. So this is a subspace of R3. Okay, both of these are planes. And suppose that I have this basis V1, which is 1, negative 1, 0. Now we can check that V1 is an element of V because when x is 1, y is negative 1, and z is 0, you do in fact have x plus y plus z equals 0. And V2, say, is this vector 1, 0, negative 1. That's also in your space V. And I see that V1 and V2 are linearly independent. And I know that V is two-dimensional because it's defined by one linear equation in R3. So V1, V2 is in fact the basis for V. And similarly, what's the dimension of W? 2, right? It's defined by one linear equation in R3. 3 minus 1, that's 2. So to come up with a basis for W, I just need 2 linearly independent vectors that satisfy the equation. So W1, let's take 3, 0, negative 1. Okay, that's in W. And let's take W2 to be 1, -1, -1. Now we can check that that's also in W because 1 minus 2 times -1 is 3, and then 3 plus 3 times -1 is 0. So suppose that this is my basis, right? V1, V2 is my ordered basis for V. W1, W2 is my basis for W. And suppose that T of V1 is 4, -1, -2. And T of V2 is 5, 1, -1. What is the matrix of T relative to these bases, V1, V2, and W1, W2? Well, in the previous example, it was easy because the question told you what T of V1 and T of V2 were relative to W1 and W2, right? You were just told that T of V1 was 6 V1 plus 3 W2, and you were told that T of V2 was 2 W1 minus 5 W2, and that allowed you to immediately figure out what this matrix is. In this problem, you're given the bases, but you're told what the outputs are just in R3, and it's not written as a linear combination of W1 and W2. So what do you think we're going to have to do? We're going to need to figure out how to represent these outputs as linear combinations of W1 and W2. Okay, well we know how to do that, right? So let's look at this first vector. Okay, 4, -1, -2. How do we write it as a linear combination of W1 and W2? Well, remember, if I form this matrix with columns W1 and W2, and if this vector 4, -1, -2 is C1 W1 plus C2 W2, then that's the same as taking this matrix and multiplying it by this vector, right? Because remember, the way we define matrix times a vector is you take, this is going to be C1 of the first column plus C2 of the second column. Okay, and we need to solve this, and we can just do the augmented matrix. So you get this augmented matrix. And I'm just going to skip the steps and just go straight to the echelon form because I'm assuming that at this point we know how to do this. So when you do it, you're going to get 1, 1, like this. And so therefore C1 is 1 and C2 is 1. And you can even check that this is in fact true because if you take this first column and then at the second column you do in fact get T of V1. Okay, now let's do the same thing for T of V2. So this was T of V1. Okay, T of V2 is, what was it? 5, 1, -1. And again, we can just do the same thing with the augmented matrix. Or you can just do the line if you, okay, just do the line, and then when you row reduce, you're going to get 2, -1, 0. And so the solution is D1 is 2, D2 is -1. And in fact, again, you can check that if you take 2 of this first if you take 2W1 minus W2, you do in fact get T of E2. Okay? So T of V1 is W1 plus W2. Okay, so therefore our matrix, the matrix we want is the matrix A, which is, so we take T of V1, it's W1 plus W2, so it's 1, 1, and then T of V2 is 2W1 plus negative 1W2, and that's our matrix. Okay. By the way, it's maybe not something I'll make a big deal out of, but notice that we did two separate row reductions. We did one here and we did one here, but hopefully when you learned about finding the inverse of a matrix, you learned that you can actually do this in one step instead of taking two augmented matrices with, augmenting. You take this matrix and then you augment it by one column vector and then the same matrix and then augment it with another column vector. You could just take this matrix and then put the two columns together on the right. So you augment it with two columns and then row reduce, because you end up doing the same row reduction steps to the coefficient matrix. Okay. And that came up in the discussion of the inverse of a matrix. Anyway, so we could have saved some time, but okay. So anyway, that's the matrix of this linear transformation. So here we had, in the examples we did, we had n equals m, and they were both 2. But in general, you don't need to do that. So in general, now we can say what to do in general. If you have some linear transformation from V to W, and let's say that V1 through Vn is the basis for V, and W1 through Wm is the basis for W, then the matrix, so now we're ready for the general definition, the matrix of T with respect to, so let's call this basis B, and let's call this basis C, with respect to B and C is okay, how do I put this? You take T of V1 through T of Vn, and you find the coordinates of these guys relative to the basis C. Okay, this isn't, this is nonsense. So, okay, but you understand what I'm trying to say. I take T of V1, I express it in terms of the basis W1 through Wm. That gives me my first column. And then the nth column, in general, the jth column, right, the jth column is just T of Vj relative to the basis W1 through Wm. I guess one way to put it is it's the matrix whose jth column is T of Vj relative to the basis C. That would be a precise way of stating it. Right? That's the definition. That definition makes sense. Okay, so in particular, let's look at the example that hopefully we're familiar with. Let's say that V is itself Rn and W is Rm. Right? And let's say that you have the basis B, which is just E1 through En, and you take the basis C, which is E1 through Em. So these are the standard bases for Rn, right? Well, then, okay, then the matrix, So let's say that T is a linear transformation from V to W. Then the matrix of T relative to these bases is, well, let's think about it. So you take the first column is T of E1 relative to the basis E1 through EM. Well, that's just T of E1. So and similarly for all the other columns. And so the matrix of T relative to these bases is just the matrix where you just make your first column T of E1, the second column is T of E2, the jth column is T of EJ, right? So it's like this. And so that's the matrix that you may have learned about when you have a linear transformation from Rn to Rm, right? And how do you get a matrix out of it? That's called the standard matrix. So this is the standard matrix of the linear transformation T. By the way, what are the dimensions of this matrix? If I have a linear transformation from an n-dimensional, I have an n-dimensional, what's going on? I have an n-dimensional domain, an m-dimensional codomain, then my matrix has m rows, right? Has m rows, and it has n columns. So this is an m by n matrix. The matrix of T relative to these bases. And yeah, that pretty much explains all there is to explain about the standard matrix, or just the matrix of T relative to the bases. So the bottom line is, if you have a linear transformation from a vector space V to a vector space W, and you choose a basis for the domain and the basis for the codomain, then not only can you represent the vectors in V and W with respect to coordinates, right, with coordinate vectors, but you can also represent the linear transformation T from V to W by a matrix. And if you choose different bases for V and W, you're going to get different matrices, just like you get different coordinate vectors. Okay. And so when you have one linear transformation, you can actually get lots of different matrices that represent the same linear transformation by choosing different bases. And maybe I should connect what we're talking about with the coordinate vectors. So let's just draw a little kind of schematic picture. So you have this vector space V and some vector space W and a linear transformation T, and you choose an ordered basis B for V and an ordered basis C for W, and that defines a map from V to Rn, and it's a one-to-one onto map. It takes V onto Rn, and it's a one-to-one map. There's no way you can take two distinct elements of V and get the same element of Rn. So this is what's called an isomorphism. Yeah, okay, maybe I won't use that term. Okay, but it basically identifies V with Rn, and an ordered basis C for W identifies W with Rm, right? And this matrix that we found, the matrix of T relative to B and C, is the matrix that takes the coordinate vectors to the coordinate vectors, right, of V and W. So you have this matrix A, okay, and yeah, it's gonna take Rn to Rm. Maybe one way to see why this is true is, let's say you take V1 through Vn to be your basis B, well then this this transformation is going to send V1 through Vn to E1 through En. And so this linear transformation is going to take V1 through Vn to T of V1 through T of Vn. And each of those is going to have a representative in terms of the basis C. So these are going to go to T of V1 relative to C, to T of Vn relative to C, right? And now the matrix A will take E1 through En to precisely those vectors by the way we defined it, right? By the way we defined it here. Okay, this is one of those things where you kind of just have to play with different examples. Like no amount of someone trying to explain this is going to make it any clearer. So just play around with some examples, find the standard basis, not the standard basis, find the matrices of the linear transformation with respect to these bases, and then once you see enough examples, you'll understand what's going on. Okay, thanks.